We are now dealing with another fluid mechanics problem, and this is still on the properties or characteristics of fluids problem, particularly on the property of surface tension. Surface tension forces can be strong enough to allow a double-edged steel razor blade to float on water, but a single-edged blade will sink. Assume that the surface tension forces act at an angle theta, or this is the assumption that you have to make, relative to the water surface as shown in the figure. For case A, the mass of a double-edged blade is given to be 0.64 times 10 to the negative 3 kilograms, and the total length of its side is 206 millimeters. Determine the value of theta required to maintain equilibrium. So this is what you are going to find, the value of your angle theta. So that's very big. I just have to change that to this one. Determine the value of your angle theta, which is in this illustration, this one here, to maintain equilibrium between the blade weight and the resultant surface tension force. For case B, and this is the case for a single edged blade with a mass of 2.61 times 10 to the negative 3 kilograms and having a total length of its side equal to 154 millimeters. You have to explain why this blade sinks, and you have to support your answer with the necessary calculation. Now, for ease of our solution, for particularly for part A, I already have laid down ahead some of the constants which we will be needing for the solution. Firstly, we have the surface tension of your water, which is given at 7.34 times 10 to the negative 2 newtons per meters. And we have also the specific weight of water, and you will see why there is specific weight or why we need specific weight of water, which is 9.80 times 10 to the 3 newtons per cubic meter. And for the case A, the given mass is in kilograms, which is 0.64 times 10 to the negative 3 kilograms. And the length, the total length is 206 millimeters. I just did a little bit of basic conversion into meters so that we will be, that's really equal, so that we will be dealing with SI units. And as you can see here, we are trying to find the angle theta. Now, the same with every physics problem, the first thing that you probably have learned is to have the free body diagram. Now, the free body diagram in this case looks like this one. So maybe I'll start with drawing the axis. So if this is my y-axis and this one here is my x-axis, I just have to put some arrow and define my axis. This is my x and this is y. Now, the thing that you should see there is if you try to look into the illustration above class, you have that there as my y, I have it over here as my x. What is, or what should be apparent to you is the fact that, um, okay, just to avoid confusion, I'll just have the axis drawn in this, in the middle part. So if I have this, an axis is drawn here. So basically, it's very clear that the weight of the blade will be trying to pull it down, or it's towards the center of the earth. So that's just straight down. And then another thing, what's keeping it suspended or at rest or in equilibrium on the water surface is the surface tension force. So that surface tension force, let's try to denote as with T, is acting on the blade at some angle theta over there. So that is trying to tell you that there is a component for the tension force. So I'm just going to re-illustrate that here. So that means that this is my surface tension force, which is the force due to the surface tension of the water that is trying to suspend it or to make it float over the water surface. So that also means that I have in here as my, that's my y component, right? So that would be my t sub y, and of course I have some angle theta over here, and this side here is my t sub x, meaning the x component of the surface tension force. I would just like to emphasize again that that is being held by the surface tension force T, not the surface tension itself. All right. So and also another force, I'm just going to denote it with another color, is the force due to the weight of the blade, and that is straight down. So that would be your first step. You have to sketch the free body diagram, and clearly the second step would be to set up the equations of motion. Now, when you take the sum of the forces along y, and of course from the Newton's second law, that is just ma sub y. So I'm not very strict. Okay, I just have to illustrate that these are vectors, so I'm gonna put some arrowhead over there, and maybe I am trying to, for my class, maybe you could do the same. Okay. So for all the forces existing on y, I'm going to highlight. Firstly, I have my t sub y because that is situated along the y-axis, and my w, or the weight. So I'm going to write it here. The fact that t sub y is on the positive y means going up, so that will bear a positive sign. Ty, and then my weight is going down, so that will have a negative sign. And everything will be equal to ma sub y. Now, a very beautiful thing that you have to note of this problem is the fact that um, you have zero acceleration because basically you're trying to find theta when your what's this, your blade is practically at rest. So at rest it means zero acceleration, so the right hand side will just be zero. So what you are dealing with basically is just this t sub y minus omega is equal to zero. So I'm just gonna write that one, minus omega is equal to zero. Now you have to recall, how do you get this t sub y, right? T sub y, how do you get that? So from your, like, recall your geometry class. So basically, the mnemonics saw and ka will help you. And when you try to look into that one, the first question, which I always say to my class, is to simply ask yourself what is the relationship of the angle theta and that specific component, in that case t sub y. So clearly they are opposite with each other. So opposite, the one that is having opposite on the mnemonic is so. So that is telling me that the sine of the angle theta is just equal to the opposite, which in that case is ty. And then the hypotenuse, of course, if this is 90 degrees, hypotenuse is always opposite to the 90 degrees, so that's your t. So this is telling me that ty is just surface tension force t multiplied by the sine of theta. So from that equation, I'm gonna substitute this one above. Okay, so what I'm working with is t sine of theta minus the weight is equal to 0. Okay, so this is a good sign that theta is already appearing. That means to say we're on the correct path, or we're nearing the completion of our solution. So from this one, what you are going to do is to, what you do in math, you transpose the w on the other side, and after doing that, you multiply both sides by 1 over t, right? So when you perform 1 over t both sides, or multiply 1 over t both sides, you are left with the sine of angle theta is just equal to w over t, right? Okay, w over t. And after that, I want to get rid of sine because I only want to take theta. So again, this is just a recall in your probably in your trigonometry class, that when you have the sine of your angle theta and you just want theta alone, what you are going to do is to take the arc sine, or the sine inverse of theta, and that will just give you theta. So that is exactly what you are going to do here. I'm just going to use red for emphasis. I'm going to take the sine inverse of that. And when I do that, what will happen to my left-hand side of the equation is just theta is equal to the sine inverse of my weight all over the surface tension force. So that's the equation that I'm now working with, which is clear and very simple. So the sine of theta, now the weight, take note, the weight is just the mass multiplied by the acceleration due to gravity. So that's very basic from your high school probably. And you have to remember from the definition, again, I'm using blue. that your surface tension represented by sigma is the intensity of your molecular attraction F all over the unit area or unit length. Okay, so that means to say that in this case, our F is represented by T and L. Now, L is given in the problem. Now, this implies that your surface tension force is just equal to the surface tension, which is the constant multiplied by length L. So I'm going to substitute that here in my equation. I have the surface tension multiplied by L. Okay, that's too long. Let's have to erase that one. So that is the equation now that I am working with. So next is to check, try to check whether these quantities are something that we don't have any problem, or is it given in the problem. Mass, okay, that's given in the problem. It's specified here that it has a mass of 0.64 times 10 to the negative 3 kilograms. G, of course, this is a problem on Earth, so G is 9.8 meters per second squared. And your theta, of course, this is just the surface tension of water, which is 7.34 times 10 to the negative 2. And your length is also given in the problem, and that is, I don't know, it's 206 times 10 to the negative 3 meters. So from here, you're just gonna have to substitute everything. So I'm just gonna write it, sine inverse. And again, do not try to underestimate the sign because it will help you check your answers. So I'm just gonna substitute the mass is 0.64 times 10 to the negative 3 kilograms, and then you multiply it by the acceleration due to gravity, 9.8 meters per square second, second squared, divided by the surface tension, which is 7.34. 7.34 kilograms. Oh, no, no, sorry. 7.34 times 10 to the negative 2. That's 10 to the negative 2 Newton over meter. And then the length is just 206 times 10 to the negative 3. So I just did some conversion of units there into SI because the original given was in millimeters. And that's not gonna help us if we're using millimeters in our equation. Now, take note that you are taking the sine inverse. So what you should be expecting, or one way to check, is this entire thing should yield no unit. That means this will become dimensionless. That is the only way that you can get a sensible quantity for the sine inverse when you're dealing it when you're trying to apply it to a pure number. Now, to check what happens in your units, I'm just going to write it in blue again so that you won't be disoriented. Your kilogram will just be written here, kilograms and meters per second squared. This is actually 1 Newton. Okay, because 1 Newton is the force required to accelerate 1 kilogram into 1 meter per second squared acceleration. So basically what you are seeing in the denominator is a numerator. I mean, in the numerator is just a Newton. That means to say this one here is just Newton. So when there is Newton in the numerator, there is also Newton in the denominator that will cancel out. And take note, what is left is the meters in the denominator of the first term, this one. And then you have meters on the numerator because basically this is a whole number. So your meters also will cancel out. Now take note that it is leaving you with a dimensionless number, and that is a good sign that you are dealing with the correct equation. Because as I said, the only thing for sine inverse to be sensible is if you're trying to take the sine inverse of just a number, okay? Without any unit. Now, if you try to do your calculation, that will give you approximately 0.4148. And then basically, when you take the sine inverse of 0.4148, that will give you this angle 24.51 degrees. That means to say that from the illustration above, this angle must be at 24.51 degrees Celsius. Sorry, not Celsius. 24.51 degrees for the surface tension force to be able to hold the double-edged blade with a mass of 0.64 times 10 to the negative 3 kilograms. Alright, so this is it. That's the minimum angle that it must be for it to hold. Now let's proceed to the problem B. Again, the problem B is basically, or the part B is basically telling us about the case of a single edge blade with that mass and this length here. And you have to explain why it sinks. So again, by the way, the thing that I should have probably mentioned earlier is this one. I'll just write it here. Condition to float. For this blade to float, it must be in static equilibrium, right? That means to say that the sum of the forces along y must be 0. Or another way of thinking is that the weight should be supported by the tension force. This is the surface tension force. All right. So by the way, that's why I try to like talk about this, because that will be, or this will be, a very essential part of the analysis of the problem B. So in problem B, recall again the condition to float is that the weight must be supported by the surface tension force. Now let's try to check whether that will be true for this case where we are dealing with a single blade, and the single blade has this given mass here and given length. So let's try to check whether the weight will be equal to the surface tension force. And of course, I will just write T sub y here. I'm hoping you understand, or it's clear why I'm just referring to the T sub y in that case. No. Sorry. All right. I was hung up from the first problem. It should just be the tension force, okay? So the weight of this one will just be m multiplied by the acceleration due to gravity is equal to, again, this is just a recall. I have actually have written this above. The surface tension is defined as the intensity of your molecular attraction per given unit length, or in this case, that is just the T all over L. So this is telling you that your T again is just surface tension times L. Okay, so let's try to continue. That is just surface tension of water times L. Now the mass is 2.61 kilograms. Okay, I forgot the to the negative 3. Negative 3 kilograms. The acceleration due to gravity on Earth is 9.8 meters per second squared. And then the surface tension of water is a given 7.34 times 10 to the negative 7.34 times 10 to the power of negative 2, that is newtons per meter, multiplied by the length. So the length is a 154 times 10 to the negative 3 meters, or originally in the problem it was given as 153 millimeters. So I just did some very basic conversion of units from millimeters to meters. So I'm gonna write here meters, 54 times 10 to the power of negative 3 meters. So let's check whether the units balance out or is equivalent on the left and right hand. Meters will cancel out, leaving behind Newton. In this case, as I've said, kilograms times meter per second squared. This is something that I mentioned earlier, that is just Newton. Yes, I want a perfect square. Okay, that is just your Newton. So basically Newton and Newton. We don't have a problem with our units, and once you do your calculation, you will get that this is just 0.0113036 Newton, and then 0.02557 and 78 newtons. So as you can see, it is very clear that this is not equal at all. So dili sila equal. And then what is more stronger, kumbaga nga force in this case, is just try to look at, is it the weight or the tension? So clearly it is 0.01 versus 0.02. So your weight, okay, I actually had this interchange, by the way. Sorry about that. Uh, Probably you're wondering why you have opposite direction. So actually that's the correct order. So this one here is 0.02 and this one here is 0.01. Now clearly, as I've said, they are not equal, and this is telling you that the quantity on your left hand side, the weight is actually greater than your tension force. So that did not establish any like static equilibrium where the weight will just be equal to T. So you can see here your weight is actually large, very large, or maybe let's illustrate it by that one. Very large going down, and your surface tension force is relatively small. So that means to say that the weight overpowers the surface tension force, so it will eventually sink. So this implies that it will sink. Okay, so that's it for this problem, and if you have some questions, maybe try to drop it down.